Okay, so let's get started. So it will be nice if, in addition to Charles, others can turn on their video. They repeat, they always ask in every class. So the topic today is this chapter on NP completeness. And as I already implied, it's really something different than what you have experienced, not only in this class, but in your typical engineering education. And I'll try to articulate the differences and why it requires a somewhat different mindset. So NP completeness, I'm not even spelling now what it means because the NP, it's a mistake to understand it as not polynomial. That's not the correct interpretation of NP, okay? So some people think that that's the correct interpretation because of the aspiration, but that's not what it means. So I'll of course spell it out as we go. Okay. So I'm going to go through a bunch of slides, which you can consider more as an atmosphere slides. You know, they are going to give you the sense, or some prepare you for the main technical claims in this chapter, and we'll put them in context. Okay, so what is this chapter all about? Up to now, we had a very clear goal. You had a problem, and you were supposed to give an algorithm, and the algorithm was supposed to be as efficient as possible for it. Of course, we had also data structures, but they were supporting algorithms. They were, in many ways, the same type of animal. And the question that is being asked at the outset in this chapter is, I give you a problem A, which looks the same as problems we have seen before. Here is the input, compute me, I don't know, find the shortest path, or sort the input, or whatever. And the question, is it always possible to give an efficient algorithm? So efficient had a slightly different meaning in prior chapters than here. In prior chapters, we wanted the best worst case behavior, and we made, and to us, an algorithm that ran in n square time instead of n cube was considered more efficient. So we wanted the most efficient algorithm, but when we use the term efficient without most efficient, just efficient versus non-efficient, the meaning in this particular chapter will be efficient is if it has polynomial runtime, and it's non-efficient if it does not have a polynomial runtime. So this will be the first order meaning. So now we are not talking about more efficient, we are talking more about black and white. Okay, so only two classes. So that's the theory translation, or the complexity theory, I would say, because everything that we study in this class is considered theory. Even the worst case asymptotic behavior is considered theory in computer science and engineering. But when we talk about the complexity theory translation, which we are going to use in this chapter, efficient means polynomial time, and if it's not polynomial time, it's considered not efficient. So the question that we ask is there a polynomial time algorithm for the problem? Or for A, I mean, this is an error, it should have been A. Or is A in the class P? it's the same thing. So P is the class of all problems that have a polynomial time algorithm. So it's the same question, just to clarify. So what is the state of the art? State of the art is that we have a positive answer for many problems, but the state of the art is also a bit frustrating because we really don't have problems for which we say the answer is no exclamation mark, meaning definitely not in P. So it turns out that the best answer that the state of the art provides is probably not. And a big part of understanding this chapter is understanding the mathematical meaning of probably not. Especially the probably, of course, here. This will be a big deal. So what does probably mean? So we are going to define some complexity class. It will be the NP complete class. And by proving that a problem belongs in it, this will be a way to argue that it's probably not in P. So what is this class? How we are going to prove it is all part of this chapter. So hold on. I'm just sort of warming you up towards the content. Given a problem A, we know how to prove it's in P. We just give an algorithm. And the big topic here will be how to prove that it's in the class NP complete or in the set of NP complete problems. And of course, we need to define that. And so there is a lot of work ahead of that. Now you can say, and here, part of this warming up slides is to give you a hint on how subtle and involved and complex and non-obvious is this whole theory about, and hopefully you will also appreciate the theory because you will see that it takes problems which do not look so different, and still it tells you for this problem we have a pretty efficient algorithm. Not only that it's efficient in the P versus NP, but it's actually have low complexity and so on. And for the other problem, we have no clue how to give any polynomial time algorithm for it. So I'm going now to give you several problems that on the face sound very, very similar. Still, one has an efficient algorithm and the other probably not. So we are going to discuss now 3 pairs of problems. Each pair sounds very, very similar. And I'm going just to report to you for now that in terms of providing an efficient algorithm, they are complete opposites. So one problem is give me a graph, find the shortest simple path. So from one vertex to all the others, it doesn't matter. We saw that all the algorithm, all of them had all pair shortest paths, all had this basically polynomial time algorithm. So let's say single source shortest. So we already know that this problem has an efficient algorithm. We studied it, right? In chapter 24, say. But what about the problem of figuring out the longest simple path in a graph? So simple path means that the graph cannot contain any vertex more than once. And I ask you to find now the longest simple path in the graph. Doesn't sound too different, right? Still, this problem probably does not have a polynomial time algorithm. Second problem, Euler tours on graphs. Euler tours on graphs, to remind you, it's a tour that may not exist, but if it exists, it will go through all the edges of the graphs exactly once. and include all of them, right? Go so all the edges exactly once. Does this problem have a polynomial time algorithm? We studied it, right? We studied it, both to the distinction when we have it, and if we have it, how to compute it in a pretty efficient algorithm. What is a Hamilton cycle? A Hamilton cycle is the same question, meaning, can you find a simple cycle that goes through all, and now the all will be all the vertices, and include all of them exactly once. Okay, so here Euler 2 is all the edges. Hamilton cycle is all the vertices. So can you find a cycle that will start at the vertex, go through all the others, include all of them exactly once, and come back to the original node? Turns out that this problem is NP-complete, meaning it probably does not have a polynomial time algorithm. So I hope that the point of this pair is clear. They sound the same. All edges exactly once, all vertices exactly once. This has an efficient algorithm, this does not. Okay, the next group of problems come from logic. And they are considered, they are known by the name. So first, what is CNF? CNF is an acronym standing for conjunctive normal form. So what does it mean? It means that you can have literals, like a variable, and the variable can appear as is or with a not. So x1, not x2, here not x1, x3, and so on. So you have these literals, which are variables, either negated or not. So each variable can be a bit. It's a 0 or 1, or true or false. So for CNF, the formula can be only of the following form, that you have parentheses. In the parentheses, the lowest level of parentheses, so the depth of parentheses is 2. The lowest level includes ors, or, and between the ors, you can have ends. So a CNF formula is an end of ors. So it's a 2-level formula where the higher level is an end across all the parentheses. And within a parenthesis, you can only have ors, and each literal can be a variable or its negation. Okay, so this is a conjunctive normal formula. And so what is a 2CNF versus a 3CNF? A 2CNF is what we have here, where within every parenthesis, we are allowed to have exactly 2 literals. So observe here, in this we have x1 and not x2, so 2 literals. Here we have not x1 on x3, so we have x1 and x3 as the variables. So in each we can have only 2 variables, x2 and x3. Okay? And it's considered 2 because you are allowed to have only 2 literals. Literal is a variable with either negation or non-negation, or without a negation. Okay. So what is 3CNF? 3CNF will allow me to have in each of these set of parentheses 3 literals instead of 2. So here, for example, it can be x1 or not x2 or x4. Okay, so you should have 3 literals per paren. And the same here. You're allowed to have 3 and 3 here. Okay. Is there anybody else? I mean, just one student suddenly asked to be admitted. I'm trying to see if there is anybody else. Ahmed, were you waiting a long time there? Ahmed, were you waiting a long time? Okay, I don't understand. Okay, so he doesn't hear me. So, okay. So, decision problem. Oh, okay. Oh, yeah, I forgot. After describing the formula, I didn't tell you what the problem is, right? So what is the problem? The problem is I give you a formula, and the question is, can you satisfy it? Oh, okay. Okay, now there is one more student who wanted to join. Oh. Okay. Okay, yeah. Okay, so what is the problem? The problem is I'm giving you such a formula, and the question is, can it be satisfied? What does it mean, satisfying a logic formula of this type? It means, can you assign truth values to x1, x2, x3, so that the overall formula will be correct? Okay, so why is it so simple, or not very difficult, if you will, to give an efficient algorithm to 2CNF? The answer is that if you assign a truth value to x1, suppose you assign to it a false. If you assign false to f1, what do you force x2 to be? You assign it to be false, right? Because the only way to satisfy this parenthesis or this clause will be by having not x1 true. So once so by the virtue of assigning a false value to any variable, you already create a domino effect where you can run with it and eliminate a certain number of clauses. So this is the mindset that will lead you to an efficient algorithm. Turns out that for 3CNF, the problem is NP complete. So they sound very similar. The only difference, 2 versus 3. Turns out that 2 is easy, 3 throws you into a completely different universe. Okay, so the point of listing these 3 problems is to give you a sense of how subtle and sophisticated and actually requires you to learn very carefully this concept of NP complete, because you will get problems that sound almost the same. And the difference between you, if you master this topic, and somebody else is that you will be able to say, to your boss, you want me to give you an efficient algorithm, but nobody knows to give an efficient algorithm today. It's a much better place to be than not knowing and feeling that you are incompetent, or even worse, having your boss think that you are incompetent. Right? So this is no fun. So here you can actually build a case to show that you haven't solved this problem for good reasons, or maybe you need to narrow down the problem to something that may have an efficient algorithm, but the narrowing down is not because you're incompetent, it's because nobody knows to solve the problem as presented to you efficiently. Okay, so this is quite an important skill that we study here, in spite of the fact that the main outcome of this skill is just to show you that you may not be able to do something, as opposed to doing it. Okay. So if we look at the difference between the first problem and the second two, I would like to observe here something which is more fundamental, which is an important attribute that will play a role down the road. So if I ask you, find the shortest simple path, your output is going to be a path. Here, or the longest simple path. If I ask you to give me an Euler tour or a Hamilton cycle, you can look at it in two ways. One is give you actually the tour or the cycle if it exists. The other way of looking at it is I'm giving you a graph, tell me if it has an Euler tour or it has a Hamilton cycle. Now, the point is that by looking at it in this way, where the answer is going to be a yes-no answer, you move the problem from an optimization problem, find shortest path, to a decision problem, because in a decision problem, the answer is a yes or no. The answer at the end will be yes, no. So when it's a yes, no answer, it's a decision problem. Similarly here, you can look at this problem of satisfying a CNF formula or a logic formula in two ways. One is tell me how you're satisfied, but the other is can you satisfy? And if you ask can you satisfy it, obviously the answer is going to be a yes, no answer. So it will be convenient for us to move from optimization problem, which characterized most of our problems definition up to now, to decision problem. You may wonder why. The answer to that, I have to defer it, but you will need from now on to ask, to switch to the mindset of decision problem. And the claim is that these are not really different problems. They are just different outlook on the same problems. For example, if I ask you, what is the shortest path between S and T in a graph, between vertex S and S and T, and then it's an optimization problem. But if I ask you, and including my input, a length K, and I ask you, do you have a path whose length is at most K between S and T? This question has a yes or no answer. And since you can do some binary search, and binary search doesn't include increase by more than a factor of logarithmic factor, in a fundamental complexity sense, the switch to decision problems is not going to be a qualitative difference, because we'll be able to show, if we can solve the decision problem, we'll be able to solve the respective optimization problem and vice versa. But we are going to make this distinction for reasons that will become clear later. They have to do with the mathematical setting in which we are going to phrase our claims and proofs. Okay, another concept which we are going to use, which the way I present it here, we look intuitive, but we are going to use it in a far less intuitive way, is the notion of reductions. So what is a reduction? A reduction is the following concept. Consider two decision problems. Problem B which has a yes/no answer. And suppose I have an algorithm that decides B, meaning an algorithm that if you give it a legitimate input for B, it will tell you yes or no. Okay. Now, suppose we have such polynomial time algorithm. Now, you really want to solve problem A. So what is the most natural way of solving problem A, which is also a decision problem? Just solve it. Give an algorithm, a polynomial time algorithm that will tell you yes, no. The notion of reduction suggests a different concept where you reduce problem in any input to problem A to an input of problem B in such a way that if the answer to this was yes, the answer to this will be yes. And if the answer to this is no, the answer to this will be no. Okay, I'm going to give you an example. And the example is really trivial. Consider the problem of 2 CNF and 3 CNF. Okay. And I already told you that 3 CNF does not have a polynomial time algorithm, but now I'm going to sort of be as inconsistent can be, and I'm going to tell you, let's assume that 3 CNF has a polynomial time algorithm. Okay, suppose, just for the sake of discussion, okay? The only reason I'm doing that is because I wanted to demonstrate to you that I can give a reduction from 2 CNF to 3 CNF. How will the reduction be? So what is the situation with every input to 2 CNF? It has 2 literals, right? So now let's assume that I'm going to do the following stupid thing, which is to look at the second literal and include it the same. So instead of having x1 or not x2, to have now or not x2. Did I extend the number of literals in this clause from 2 to 3? I did. But I did something completely stupid, right? Because I really duplicated this literal. So whatever satisfied this literal before will satisfy it now. And whatever didn't satisfy it will not satisfy it now. So we have really done nothing. It's an exercise in futility, if you will, right? But what I showed you is a formally correct reduction from 2 CNF to 3 CNF. The time for doing the reduction is trivial. You know, you just go every clause and you do this stupid thing. So the time is obviously polynomial. So this is definitely a correct reduction because every input that should have satisfied A will go to an input that should satisfy B. Okay? And now, to the extent that you will be able to give me a polynomial time algorithm for B, you have an overall polynomial time algorithm for A as well. Okay, so the point, so that's the point of this concept of reduction. Obviously, in some cases, it makes sense. But what I want you to remember is that we switched now not to the constructive side of the course where we give algorithms, but to the part of the course where we try to argue that a problem is difficult. So what if, oh yeah, I started adding it and I don't know, it disappeared to me. I did it last night and so, okay. What if A does not, what if, let's see, what if A is not in P. Okay, so suppose now that I gave you a reduction from a problem A to a problem B, okay? You know that A does not have, you proved it, hypothetically. Suppose we prove that A does not have, is not in P, does not have a polynomial time solution. But you gave a reduction to B. Now you have no idea how B will be, meaning does it have a polynomial time algorithm or not? What can you conclude from what I just told you? That suppose I know that A does not have a polynomial time algorithm, and that I built for you a polynomial time reduction from any input of A to any input of B. What can you tell me about B? So let me ask you a more specific question. Can B have a polynomial time algorithm? Again, I told you A does not have a polynomial time algorithm. So suppose that A does not have a polynomial time algorithm. Suppose that I gave you a polynomial time reduction from A to B. Is it possible that B will have a polynomial time algorithm? It is possible or not? Think about it. If B has a polynomial time algorithm, if we combine the two, you get a polynomial time algorithm for a contradiction. Do you follow me? Again, write it to yourself. A does not have a polynomial time algorithm, assumption number one. Assumption two, I gave you a polynomial time reduction from A to B. What can you tell me about the prospects of having a polynomial time algorithm for B? I claim that it is impossible because if you give me a polynomial time algorithm for B, it implies a polynomial time algorithm for A, which we assume is impossible. Follow me? So look at the very subtle, and in a way, this is going to be a huge trap for students in this course, I can assure you based on prior years. Having problem B, having a problem B easy implies that problem A is busy. But having problem A difficult implies that problem B is difficult. You see what I'm saying? So the ease flows from B to A. The difficulty follows from A to B. Confusing, right? But did you follow my more rigorous argument? Please don't hesitate to ask if you have any question. So this is actually a pretty cool observation, which, as we are going to see, is going to play a huge role in this chapter. I'm going to visit it and revisit it and revisit it, okay? So, but that's my first opportunity to highlight that. And for that reason, I wanted to say it as early as possible. because I just want you to understand my methodology of presentation here. I could go through the full mathematical assumptions, take you through all of them, and then start throwing at you corollaries. What I'm trying to do here, I'm trying to make a stop and convey to you the main ideas in this chapter at the earliest possible time in which I can share this idea with you. I just think that this is better for you understanding, because instead of not understanding anything up to the end of class and then suddenly put things in perspective, I'm trying to build it with you as we go. So your understanding at this point is limited, but it is, I believe, bigger than had I just skipped on it, defined the notion of reduction and ran forward. Okay, so that's what I'm trying to achieve. If I achieve it or not, you should know, but I'm just trying to explain my rationale behind this mode of presentation. Okay, so all of this is a pretty rigorous and formal mathematical theory. So in order to formalize it, we need to switch from the world of problems to the world of formal languages. And for that, I need to define what is a language, and then to explain what is a polynomial time algorithm in the context of a language. Okay, so what is a language? A language comprises, first of all, an alphabet. So to make things as simple as possible, think about the binary alphabet, just 0 and 1. These are all the letters in your alphabet. Okay, no more letters. What is a language? So a language first allows us to consider what's called sigma star. So sigma star is the all possible strings over the alphabet. Meaning, give me all the strings of zeros and ones of any length. So give me an alphabet, all the words or all the sentences, if you will, that you can write with these two letters, or with the letters in sigma. Okay, so this is pretty much in line with our understanding of what a language is. Okay, I'm sorry, of what an alphabet is. I'm sorry, what an alphabet is. Now, what is a language? In a language, some of the strings will make sense, others will not. So if you look at a language, if you chain a few letters, some of it will give you a word which is in the language, others will not, right? So the symbol, so the set of all strings that are, so a language alpha over is a set of strings made up of symbols in sigma, meaning a language will be a subset of all the possible strings possible, a given subset. And I'm going to give you an example. So once I give the example, I hope everything will be clear. So the language L in this example is all the prime numbers. Now, I allow you to represent numbers only using their binary representation, right? So this is 2, this is 3, this is 5, this is 7, right? So you follow me, right? So the language of prime numbers will be all the binary strings represent a number which is a prime number. Well defined, right? And the question that you will get here, which is really the type of mindset, the mindset of the new languages, or the new mindset of problems that we are going from now on discuss only in the form of languages for mathematical rigor reason, is I'm giving you an integer n, and the question is it a prime number? Or in other words, I give you an integer n, is it in L, where L is the language of prime numbers. So you see, I'm giving you an element, a string over the alphabet of the language, and I ask you, is this particular string a member of your language? Is it clear how I switched from the word familiar to you, like here's a number n, is it prime, to whether it's in your language? Meaning, is it in the language of prime numbers?
Professor.
Go ahead.
So the elements, wait, yeah. So the elements inside the L are like we have to find that they are prime numbers or not. Is that what you mean?
No, not at all. Not at all. I'm
L.
defining for
Okay.
you.
Yeah.
I'm defining for you the language to be the language of prime numbers. And I can give you whatever characterization of what is a prime number. We all know what they are, but suppose I come with a definition, okay?
Mm-hmm.
Now, so this is, I'm not yet done with the problem. Now
Okay.
I'm giving you a problem n. And I ask you, is n a prime number or not? Now, in terms of the languages, what I'm asking you, is n a member of the language of prime numbers? So first, think about this problem in the way it's familiar to you. If I ask you, I'm giving you a number, is it prime or not? Problem clear, right? No
Yeah.
problem.
Yeah.
The only
Okay.
thing you need, the only mental exercise you need to do in this particular slide is to translate this question to the setting of languages, where now prime numbers will be a language. A language is a set. And who is in the set? All the prime numbers, right?
All right. So these are the binary representation of the prime numbers.
Yes, yeah. Starting from the beginning, of course, there are many more.
Okay. Okay. So 1 0 is a prime binary number, right?
Yes.
So okay, but 1 0 in so it is actually number two, right? If
Yeah.
but okay, got it. Yeah, yeah. Got it. Okay. All right. Thank you.
Okay. So I'm not going to give you the list, of course. I'm going to give you some characterization. Okay. But I just want you to think about it as a language where a problem that previously you thought about of does it meet a certain criteria, now you need to think about it in terms, here's a set, is the next element you give me a member of the set or not? And the only thing that I want you to be convinced, and we are going to demonstrate it repeatedly again, we are just at the beginning of this chapter, why you can basically take any decision problem you can think about and actually present it as a language. We are going to see that as we go. Believe me, for now, I just gave you one example, but we're going to see that this is as powerful a way of formalizing the notion of a problem as you can get. Okay? But so is it clear for now?
Yes, sir.
Okay. Now I'm going to ask you, because you see, part of the main reason, if you will, the lead reason for considering this is for matters of efficiency, right? Remember that the lead question for us is, here's a problem, does it have a polynomial time algorithm or not? Right? This is the main question that is hovering over all this chapter, right? That's the question. Now, since we are talking about efficiency, and now that we understood how, in what way the recognition of prime numbers is a problem in the formal language sense of the word, I'm now asking you the following. Suppose I give you an algorithm whose input is some number, is some integer n, and I ask you determine whether n is a prime number. Okay, so the task for the algorithm is clear. Like, tell me yes, no. And suppose that you came up with an algorithm that gives me the answer in time which is polynomial in n. Okay? And here's the question. Question is, you gave me a number n. I gave you an algorithm that runs in time polynomial in n. Have I established that the prime number decision problem, which is what I solved for you, is in P? Because I gave you a polynomial time algorithm, an algorithm which is polynomial time in n. Okay, is the question clear? So what is the answer? Have I established that it's in P or not? I gave you a polynomial time algorithm in n. Okay, anybody wants to jump with an answer? I mean, it sort of begs an answer. Don't be shy. I really want one of you to come back and say yes, or if no, explain why no. Don't be shy. That's so you gave a polynomial time algorithm in n. And remember, we are talking about polynomial time algorithms. So does it establish that the prime number decision problem is in P?
I I can't think of a reason why it wouldn't be in P, but it seems like
Okay, right. No, so you're suspicious. You know, that's good to have this attitude. But again, okay, good. So your answer is yes, but I believe it's yes, but I know that I'm wrong or something.
correct.
Okay, right. Okay. So you have good intuition, but at the present time you don't have good reasoning, right? So which you admit. Fair enough. No, that's good. Okay. So it begs the answer. Of course, it's polynomial. What are you talking about? You're running in circles, right? That's what you would like to say. So the hint is exactly what you were got. I think that the answer is no. And the question is, how can it be no? Right? How in the hell can it be no? You want the polynomial time algorithm, you give me n and I give it polynomial time. What's wrong? Okay. Anybody wants to give it a try? How can it be not polynomial time? the polynomial time algorithm you gave. Sounds almost like an oxymoron, right? So the answer to that, so do you want me to proceed, or anybody wants to throw an answer or a guess? So the answer to that is polynomial in what? See, if I give you, it should be polynomial in the length of the input. But what is the length of the input? If I give you how many bits do I need to describe a number of size n? How many bits do I need? Log base 2 of n, right? Agree with me? So if I gave you an algorithm which is linear in n, what is its performance as a function of log of n? It is exponential, right? 2 to the log of n equals n. Does this make sense? And for that reason, an algorithm which is polynomial in n is exponential in the length of the input. And for that reason, polynomial in n does not mean that the problem is in P. Does this make sense now? So what you really need to take into account when you consider the notion, the term P in this context, is not what you interpret as the size of the problem, but you need to actually take a very close look at the encoding. And here, since the encoding is binary, I can describe to you a number, the number n, by log n bits. So log n bits is the, given this encoding, is the length of the input. And any claim of polynomiality must be as a function of log n. Okay? Make sense? Okay, so I hope I at least clarified why that polynomial time algorithm in n does not establish that prime number decision problem is in P. Okay. For languages, the set P is the set of languages, say over the binary alphabet, such that there exists an algorithm which decides L in polynomial time. Meaning, I give you a language L, I give you a member of an alleged member of L, given some encoding, and to the extent that you can identify whether this alleged member is indeed a member or not, meaning you decide L in polynomial time in that alleged member, then the problem is in P. Otherwise, you have not established that it's in P. Okay? So this was the first sort of really completely new, or maybe the second new concept. We had the concept of reduction, which what was new there is the direction of showing that something is difficult. Then we had the notion of a language. And now comes a concept which really comes out of the blue. And in my mind, it may be even the most surprising concept to learn in a course which focuses on algorithms mostly, because it will be a concept which looks as the mother of all useless concepts. Okay, and how can such an argument and such a concept be useful is really mind-boggling, but it is useful, I can tell you. But it's really funny. So what is this concept? Previously, we were talking only about algorithms, and algorithms make a lot of sense, right? You have a problem, find solution. It makes so much sense, you know, like that's what engineers do, right? They find solutions. So here is a concept which is very different than the concept of algorithms. It's related, but it's very different. It's the notion of verification. Okay, so look at this problem. Hamilton cycle problem, I already defined it. It's if you want to think about it as graph, and graphs are languages, because what is a graph? I can describe to you any graph as a sequence of bits, like the bits list all the vertices, all the edges, and so on. Okay. So now a graph which has a Hamilton cycle is in the language Ham cycle, and a graph that does not have a Hamilton cycle is not. So let me remind you what's a Hamilton cycle. Actually, here you see a Hamilton cycle. You have a graph, and the ability to actually do a cycle like the one with the shaded edges that goes through all the edges, all the vertices, come back to the first one without visiting any vertex more than once, is a Hamilton cycle. So in this case, if this is the graph you give me, it is in Hamilton cycle. But if you give me this graph, it's not very difficult to explain why it's not in Ham cycle. So let me briefly explain it. It's a bipartite graph, like boys and girls, if you will. And here you have the edges if a boy and girl like one another, for example, or something like that. And now what we would like is to have a Hamilton cycle. And the reason that we cannot have a Hamilton cycle here is because we have two more, because we have so many more vertices on this side than on this side. So if I start a walk, if I start here, I charge one to the left, one to the right, one to the left, one to the right. I run out of the left before I ran out of the right. So obviously I cannot find a cycle. So the only reason for demonstrating this is to show you that we have graphs where there are no Hamilton cycles. So I hope that this demonstrates the problem. So what is the verification in this context? The verification is the following. Give me a graph where you claim that you have a Hamilton cycle, but it's not enough that you claim it. You actually show me the Hamilton cycle, like here. Now, what will be a verification algorithm? It's an algorithm that if you give me a Hamilton cycle, or a cycle, or a path, if you will, you give me a path, I can verify that the path that you gave me is a Hamilton cycle. Is that clear? So unlike a typical problem that we are familiar with, where you are getting a graph and you are supposed to find yourself whether there is a Hamilton cycle or not, Here, I'm giving you a graph and a candidate cycle, and your only job for your algorithm is to verify that what I gave you is indeed a Hamilton cycle, which is clearly a much easier question, right? So this is what is called a verification algorithm. And the polynomial time verification will mean that you can do it in time which is polynomial in the graph. So is the notion of verification clear in this example? You give me not only the problem, but also the solution, and the only job that you need to do is to verify that this solution is correct. Now, what will be so amazing is that we are going to use this family of verification algorithm to reason on whether you can find an algorithm for a problem. This is what's so amazing. Not that we use it. It makes sense sometimes to have verification. Verification in itself is not an unnatural concept. But the fact that it's relevant for arguing or for the theory of reasoning on whether you have an algorithm for the problem for which you have verification is surprising. Okay. So now we are going to advance towards a formal definition of the class NP. And now, for the first time, I'm going to tell you what NP stands for. So NP stands for the following: non-deterministic polynomial time. Okay, so for now, this whole notion of non-determinism is completely unclear to you. But in terms of just, we use an acronym, NP. So NP means non-deterministic polynomial. So the N comes from here, the P comes from here. Okay, so for now, it's no more than a name. After I define the class NP, the name will hopefully will become clear. Okay, so now we are going to make throughout an assumption that all the inputs are binary, that the alphabet is 0, 1. And so what is a verification algorithm for a language? So a verification algorithm for a language is an algorithm. So an algorithm A is a verification algorithm if it must have 2 arguments. One argument is the ordinary input string. Like in this example, argument A will be the graph. It's vertices, edges, and so on. The second argument, Y, will be a certificate. In this example, the certificate will be the cycle itself, the path that creates a cycle. So the second argument is why it's called certificate, such that when I apply the verification algorithm to the graph and to the cycle, you conclude, yes, this cycle indeed, or the path that you gave me indeed is a Hamilton cycle. So a verification algorithm must get 2 arguments. One is the original input, and the second is the proposed solution, if you will. And it verifies that it's correct. The language verified by the verification algorithm A is all the X over this binary alphabet, such that there exists for them a Y for which AXY is 1. Okay, this is really a mouthful. So I'm giving you a verification algorithm. And the question is, what is the language that it verifies? And the answer is a roundabout answer. If you can find a certificate, and I'm not telling you how to find it, I will show you that the certificate is correct. Understand? It's like the following really useless sounding useless statement here. Telling you that I want you to find the Hamilton cycle. You'll say, and you have no clue how to do it. So I'm coming to you with the following useless suggestion, that if you give me a Hamilton cycle, I will show you that it's indeed a Hamilton cycle. Big deal. Right? Okay, so this is really the language which is verified by a verification algorithm. Okay, so it's not very useful. So the complexity class NP is the class of languages that can be verified by polynomial time algorithm. Okay, so this is really puzzling. Let's see what it says. It says what falls in the language NP. In the class NP, I'm sorry, in the class NP. I'm yet to define NP complete. Now it's only NP. It's all the languages that have a polynomial time verification algorithm. So if we go back to the 3 examples I gave you before that I told you are challenging, all of them, it will be pretty clear that there is a verification algorithm, right? Look at that. Yeah, because remember, I'm talking about decision problems. So the decision problem of a simple path will be, does your graph have a path of at least k? Clearly, this problem has a polynomial time verification, because if you give me a path, I can count how many vertices it has. If it has k or more, the answer is yes, you established it. But of course, it doesn't tell me how to find the path. Again, if you give me a Hamilton cycle, I can verify that it's indeed a Hamilton cycle. If you give me a satisfying assumption to 3CNF, I can trivially verify that it's a satisfying assumption. Right? So in all these cases, the fact that I told you that we don't have polynomial time algorithm didn't disqualify any of these problems for being in the class NP. So the class NP is actually a pretty enormous class. It includes all the problems for which we have no clue how to solve them in polynomial time. It's a much bigger class. So L is an NP if and only if there exists a 2-input polynomial time algorithm A and a constant C such that the language L includes all the x's over this binary alphabet, such as a certificate which is limited in size. It cannot be larger than a polynomial in the length of x, such that applying the verification algorithm A to A, x, and y will give you 1. Okay. So this is the class NP. It's a very confusing class for now, and I expect you to comprehend this not fully, to comprehend it fully, not at this point, but as we advance and we'll go through more examples, things will fall into place. In particular, let me highlight now the term non-determinism. Non-determinism means that I'm defining X based on some Y that you have no clue if it exists or not. So in terms of constructively solving this question or addressing this question, do you have a Y or not? What do you need to do? You basically need to try all the 2 to the whatever possibilities for a Y, because I'm not telling you what the Y is if in the normal setting here, well, it's not a verification situation. So you know that there is a verifier, meaning you know, like for example here, there is a satisfying assumption, assignment, satisfying assignment, right? But what is it? Every x1, every x2, and so on can be true or false. So if I'm only telling you that I will be able to verify it, you need to try all the 2 to the n possibilities, where n is the number of variables here, in order to use this constructively. And the fact that you need these 2 to the n possibilities, you don't know which one will work, is what stands behind non-determinism here, because it tells you that there is an answer, but we don't know how to find it. The only thing we tell you is that it's one of several. So if you try non-deterministically, meaning all of them, one of them will show up, but you don't know which one. So that's really where this name is coming from. The last term I'm going to describe today is the notion of co-NP, or complement of NP, because there will be problems where their complement is in NP. For example, if the question becomes not whether you have a Hamilton cycle, but whether you don't have a Hamilton cycle. I mean, this will be a legitimate language, right? All the graphs, they do not have a Hamilton cycle. It will be the complement, right? Because a graph can either have or not have. So co-NP is languages, their complement is in NP. Observe that a co-NP language is not necessarily in NP. And in fact, what you have here, and I'm not sure I need to go into much detail, because at this point, I have just thrown at you a huge number of definitions, and I probably confused you more than anything else. But you see here the various possible relationship between P, NP, and co-NP. One possibility is that they are all equal. In this case, the theory that we learn in this chapter is complete garbage, because the whole point will be to show that a problem is of NP complete, will be to show that a problem is not in NP complete, and for that reason is unlikely to be in P. We are going to explain the unlikely statement. The other possibility is that P equals N co-NP. You have this possibility that the intersection is smaller than each, and you have this situation where P, co-NP, and their intersection are, and this is P, by the way, that they look like that. And this is the current belief, but nobody has proven that any of these possibilities doesn't hold. We just have now almost 50 years of working on this topic with almost zero progress on figuring out which of these relationship actually holds. Okay, I think my time is up. So I'm going to resume here on Wednesday. Any questions for now? And again, I really recommend, and I'm a bit disappointed by the number of students attending. Of course, you are here, so it's not a comment to any of you. But in my opinion, it's very important to attend these lectures so that you can ask questions in real time. Because if the only thing you do is to watch the video and you have a question, I will not be there to answer. Okay. So, and sometimes you really want the answer as you understand, as you hear the terms for the first time. And of course, you are welcome to read ahead. This will definitely be helpful. Read ahead of the slides and then be ready with a question. This can also be quite effective. But if you do it after that, then you're on your own. Okay, so that's it. So we'll see you Wednesday. Bye.
Bye bye.